Hello, we are Team 16 sharing our final presentation of the analysis and redesign of an HVLP spray gun. Our team is comprised of Ethan, Nick, Steven, Peter, Keon, and Mike. This product is an HVLP spray gun, which stands for high volume, low pressure. It is a tool used to apply paint or coatings with high efficiency and control. It works by using a large volume of air at a low pressure to break the paint into a fine mist. HVLP guns are commonly used in automotive painting, woodworking, and finishing applications. These would be our primary customers. Our secondary customers would be those amongst amateurs for their artistic purposes and for smaller automotive painting projects. Here's an exploded view of our CAD with labels. The main function of this tool is to spray paint, while its sub-functions are to atomize the paint, regulate the spray, and ensure convenience and dependability. Function component mapping matrix shows that most components contribute to the primary functions of the release of paint and the airflow associated with that release. This presents an opportunity for part consolidation with these components. It can also be seen that the hanging hook does not contribute to any primary functions. This information allowed us to look for opportunities to incorporate this hanging hook into a different component. After comparing all of our functions for our primary and secondary customers, we found that only the contained paint function would be different between customers. The component that achieves this function is the paint container. Module change for a primary and secondary customer is the size of the paint container. The volume of the larger tank is 2 times the volume of the smaller tank. This larger tank would be ideal for professional use in larger scale products. Common interface for the paint container is an internal threading within the main body. An assembly sequence and a modified assembly sequence show the different container variants and the delayed differentiation within the assembly sequence.
This is our DfA manual section. Our quad chart is pictured below. We chose the axle as our platform, which is high functional importance and low manufacturing cost, and the paint container as our module, which is high functional importance and high manufacturing cost. To the right, you can see the axle, which is in green, and on the axle, there's E-clips connecting it to the trigger currently. The trigger's in orange, and the paint container is in yellow below. This is the pre-modification CAD. This is our post-modification CAD. For the axle, we went by DfA 2, reduced fasteners, and DfA 3, prefer snap fits. As you can see, we got rid of the E-clips, and the axle is now a snap fit into the trigger. For the container, we chose to modify it by DfA 1, reduce part counts. And as you can see, the modification is this little hook on top of the container, which is sort of explained in the next slide. So the hook on top of the container previously used to be the light blue part in the before CAD, and the only purpose of this part was to physically hang the gun up. So we just attached it to the top of the container. Here's our impact analysis. Pre-DfA, the assembly efficiency is about 0.3631, and post-DfA is 0.4208. So that's a pretty significant increase.
Based on the assembly sequence in the product family assembly diagram, we chose a subassembly consisting of the main body, the internal nozzle, the large knob, and the small knob. We chose the main body and the internal nozzle as both of these parts are products that correspond to high functional importance and high manufacturing costs in the quad chart. All remaining components of high functional importance could not be altered without potentially altering the core functionality, and as a result, we did not tamper with them. As a result, we altered the large and small knobs as we could easily improve handling by reducing the number of unique parts. When it came to the knobs, we made them the same to reduce overall part variety. For the main body, we added pins that could be used as locating pins, in order to provide more locating features. And for the internal nozzle, we added features in order to facilitate orientation. After redesign for auto assembly, the total cost was reduced by 10 cents from $4.86 to $4.76.
One of the redesigned components was the paint container, an aluminum part with a prismatic cylindrical geometry. The container can be manufactured using several processes, including die casting, sheet forming, and powder casting. A thickness analysis determined a minimum wall thickness of 1.4 millimeters. Considering the material, required tolerances, anticipated production volume, and critical dimension features, die casting was selected as the preferred manufacturing method for this part. The critical dimensions are featured in the images above. Another redesigned component was the internal nozzle, which regulates airflow and controls the width of the paint spray. It's made from 304 stainless steel with a prismatic cylindrical geometry, and manufacturing options considered included sheet metal forming and machining. The required surface roughness was specified as 1.6 microns based on the functional need to spray paint through a small orifice while remaining practical to produce. Given the material, tolerance, surface finish, critical dimensions, and batch size, machining was determined to be the most suitable manufacturing method for this part. For the container, the outer diameter of the common interface is a critical dimension due to the need for it to be threaded with machining post-processing. Also, the container diameter is crucial to fulfill its FCMM functions, so the tolerance will be 0.02 inches. For the nozzle, a dimensional tolerance of 0.005 inches was selected to strike a balance between performance and achievable machining accuracy for stainless steel components of this size.
Here we can see the paint container after DFA Auto and before DFM. And here are the changes we made after DFM, including changes to the wall thickness, sharp edges, uniform thickness of the wall, and more sharp edges and filleted corners. And here is a final drawing and associated dimensions of the paint container after DFA and DFM. And here we can see the cost analysis before and after DFM, with DFM saving a total of 7 cents per part.
Our initial design before design for manufacturing had some complex geometry that added time to the tooling, inner holes close to the edges, which is generally bad practice for DFM, and a long narrow hole, which is also bad practice. These bad design practices were corroborated by our analysis in DFM Pro. To fix this, we widened the long hole in the center in accordance of DFMC5, which tells us to avoid long narrow holes. According to DFMC7, we want to move holes away from edges, so we moved the radial holes towards the center of the design, closer towards the center of the design, away from the edges on the back. DFMC15 says that we should reduce tool changes by reducing complex geometry, so we removed the complex geometry of the bolt part and made the geometry more uniform from front to back. Our analytical method indicated a 32-cent reduction after our design for manufacturing, going from $1.84 to $1.52. Our Hubs estimate indicated that we went from 21.8 cents per part to 14.4 cents per part, almost a reduction to half. Here you can see where in the process the cost was reduced for the internal nozzle redesign.
The product service system that can be offered is a coating quality assurance service in which the customer not only pays for the HVLP spray gun, but a consistent high quality paint finish. The manufacturer would provide on-site or virtual training and any sort of technical help that the customer may need while they're doing their at-home projects. In conclusion, our design changes improve manufacturing costs and time. We also identified more areas of improvement, like further part consolidation. We also thought about a new approach to improving the design for manufacturing of this part.